Get started. So a math refresher. The first thing that shows up a lot in StatMech is the notion of a factorial. Normally it's written like this. Sometimes it is also written like this. Okay, I will use the exclamation mark sign. It is n multiplied by n minus 1 multiplied by n minus 2 ... till 1. You can generalize it to a gamma function for other n's. We won't be concerned with those in this class. Okay, our n will normally be integer, positive integer. So that's factorial. However, the factorial is kind of hard to calculate. And especially as we start going to thermodynamic limit, I mean, think about calculating the factorial of 10 to the power 23. It's going to be terrible, right? So one of the most heavily used approximations in this course is the Stirling's approximation, which tells us how to approximate n factorial. And it doesn't really talk about n factorial because, as you will notice, starting Tuesday and soon, often we are not interested with large numbers, we are interested with log of large numbers, right? We don't directly deal with n factorial. You will see the log shows up a lot in statistical mechanics. And so we are very interested in this quantity, which is the log of n factorial. And Stirling's approximation says that this is approximately n ln n minus n. So this is going to get used heavily. Any idea how to prove this?
Take the graph of log x and find the area under the larger end approximate. Something like that. I don't know. You take rectangles and you add their areas.
Oh, that's one way, but tell me quicker. You're telling me how the proof should look like. You're being like my advisor. Telling me, I got to do that. Huh? Taylor series, yeah, there are many ways. So the most intuitive way of thinking about it, let's do it in a couple of ways, which is the first way to think about it is that ln n factorial is actually ln of n multiplied by, yeah, if you go to Taylor series, that's the best way. Then it leads to a series known as Taylor Euler-Maclaurin series or something. Then you can get higher order terms and it gets quite beautiful, but we are not going into all that. So this is n multiplied by minus 1 multiplied by minus 2 multiplied by n minus 3 till 1, right? So what is that thing? That thing is ln n plus ln of n minus 1 plus ln of n minus 2 till ln of 1, right? So this is exact. There is no approximation here. But if I try to compare this thing with the following quantity, ln of n plus not ln of n minus 1, but again ln of n plus again ln of n plus ln of n. Which one is larger, the top one or the bottom one? Bottom one, right? Because instead of ln1, you have ln n, and we're talking only n large positive number. So this is definitely going to be smaller than this. What is this quantity that I wrote down? How many ln n's do I have over here? N, right? So this is n ln n. So you can already see that ln n factorial is going to be smaller than n ln n, right? And you can see intuitively that that's smaller, and turns out it is approximately smaller by the quantity n. So I didn't prove this, but you try to give you a sense of where it comes from. And especially as n becomes larger and larger, this part of the approximation becomes more and more rigorous, more and more accurate. You even don't have to consider the minus n, right? Because n log n is much larger than n, right? So this is one way. The other way is to, instead of Taylor series, we can do it a bit more. We can do an integral of it. For large n, we can replace the summation with an integral. And I like this trick a lot because it shows you a mathematical operation that will be showing up in statistical mechanics a whole lot. Okay, so now let's think about ln n factorial. And what is ln n factorial? Once again, it is ln of n multiplied by n minus 1 multiplied by n minus 2 till 1. Same thing. This is ln of n plus ln of n minus 1 ... plus ln of 1. So that can be written as summation m is equal to 1 to n ln m, correct? Everyone happy with this? So notice what I did over here. I have replaced ln of pi product of m going from 1 to n with sum of ln. This particular operation is going to show up like on a weekly basis or a daily basis. ln of product being replaced by sum of ln. Okay, this is a simple property of the log, right? Log of a plus b. Log of ab is equal to log of a plus log b, right? That's what we are using over here. It will show up with such frequency in StatMech that you will get confused. For Bose-Einstein, for Fermi-Dirac, this particular approximation is going to, equality is going to show up like a zillion of times. Yes, it's very important. You took photo. Good. So we have this. Now we can do an approximation. We can say it is a summation for very, very large n. Let's approximate this summation by an integral ln x dx, where x goes from 1 to n, right? And what is the integral of ln x? You have to do by parts. Yeah. The other important formula for this course. That is exactly n log n minus n. So this is another way to prove the Stirling's approximation. Okay, so but remember this formula. Many times you will have to use both terms, n ln n minus n. Try to use both. It's very rarely that you can get away with just n ln n. I have seen lots of errors happening in StatMech by people ignoring this minus n. It can lead to non-extensive properties and all sorts of funky behavior if you're not careful. So that's Stirling's formula, which is, and the concept of a factorial, which will show up a lot in this course. Next thing that you should be familiar with is the concept of permutation and combination. Okay, so basically permutation and combination in a layman manner means the number of ways of arranging things. When the order of arranging matters, it's known as a permutation. When the order of arranging does not matter, it means a combination. So this is when order of arranging matters, and this is when order of arranging does not matter. Why should we care about this? Because when we start to think about classical statistical mechanics and quantum statistical mechanics, sometimes particles will be indistinguishable, sometimes particles will not be indistinguishable, and you will have to think carefully which one to use. So when the order matters, it is written as P. So you have n things, and you have to pick m things out of n, okay? Where m is, you can make it 0 also, but basically it's 1 less than equal to m less than equal to n, okay? And this is also written as the following, npm. And the formula for this is n factorial divided by n minus m factorial, okay? So let's get some intuition for this. Let's say, so I'm feeling very hungry right now. So let's say I have, and I always want to eat dessert. So let's say there are 10 desserts. Well, deserts actually apply to, no, deserts is the bad example for this. Let's say there are 10, let's get to example in a bit. Let's first talk about combination also. So when the order of arrangement matters, it is P and M. When the order of arrangement does not matter, it is C and M. And that is written as N choose M. So instead of NCM, people often call it N choose M. How can you pick M things out of N things when the order of picking does not matter? And the formula for this is N factorial divided by N minus M factorial, same as above, but dividing by another M factorial. So when the order does not matter, you have fewer ways of picking things, okay? So let's look at 2 examples, and you guys tell me which one is permutation, which one is combination, okay? So let's say there are, how many of you are there? Like 22 of you, I think. The 22 aspiring, what do you all aspire to be? Olympic gold medalist, Olympic 100-meter winners. Okay. And I have to pick 3 for silver. Oh, why did I think of silver first? Gold, silver, and bronze. So how many ways can I pick 3 people out of 22 for this? Is it permutation or combination? It's permutation. The order matters, right? Who gets picked first goes to gold. Who gets picked second goes to gold. So this is permutation. So the answer will be 22 P3, and you can calculate it. It will be 22 factorial divided by 19 factorial, which is going to be 22 multiplied by 21 multiplied by 20, whatever that thing is. Okay. Now let's think of the desert example. I have 10 deserts, and we all went for a meal, and we have to order 3 deserts out of the 10. You might be fastidious. You might be like, I want to eat this dessert before this other dessert, but normally that's not how it works, right? You just pick 3 items and they get delivered together, right? The order does not matter. 10 desserts, and we want 3. Then it is combination, right? Any 3 matters. It does not, they are probably going to bring all 3 together, right? It does not matter what is the order. And actually, let's make it 22, just to compare with the previous example. We want 22 desserts, and we want 3 out of them. Or another way to think about it is we were not giving gold, silver, bronze. We were just giving top 3. And we are not distinguishing who is gold, silver, and bronze, right? So that will lead to more, that will lead to less arrangements or more arrangements. It will lead to less arrangements, right? Because Alex Gold, where is Homer? Homer, we already lost Homer. So I'm going to use it for an example every single time he does not come to class. So he listens to the video and he'll be like, oh my God. So let's say Alex Gold, Homer Silver, and Kinjal Bronze, right? Versus Alex Silver, Homer Gold, and Kinjal Bronze. Kinjal is always bronze. I don't know why. Those 2 are the same arrangements, right? So you have to remove that out. And the overcounting that you have done is going to be 22 factorial divided by 19 factorial divided by 3 factorial. So this one is going to be 22 multiplied by 21 multiplied by 20. Factorial of 3 is 6. So it's going to be a smaller number. So this permutation combination will show up a lot once we get to different type of statistics, you know, whether particles are distinguishable or they are not distinguishable. This will start to matter hugely. Okay. Another concept that can show up every once in a while is the binomial theorem. If you have x plus y and you want to raise it to the power n, this is where combination gets used heavily. This is going to be x to the power n plus n choose. And I forgot there is a third way to write n choose m, which is written as n round bracket 1. And I will be using all 3. I will totally confuse you. I'm sorry. Okay. For permutation, I will always use P. Anytime permutation is used. Combination, I will use any of these 3. Why? Because that's in my muscle memory. I cannot help it at this stage. N choose 1 multiplied by x to the power n minus 1 y plus n choose 2 x to the power n minus 2 multiplied by y square plus dot 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 till n choose n multiplied by y to the power n. This is binomial theorem. You know its examples for x plus y whole square. That is x square plus, you can see n choose 2. What is 2 choose 1? X to the power 2 minus 1 y plus 2 choose 2 y to the power 2. What is that? That is x square plus 2xy plus y square. You can generalize it. X plus y whole cube is going to be x cube plus 3x square y plus 3xy square plus 3xy I think plus y cube, something like that. Okay. I'll put a check here because I might be wrong. But remember binomial theorem, then you can compute whatever you want. Okay. Sometimes I don't think we'll use multinomial theorem, which is something like x plus y plus z plus to the power n is equal to what? This is known as multinomial theorem. Look it up on Wiki. You can think of it partwise as binomial, right? X plus y and z in binomial, and then x plus y inside, right? That's the whole idea. The next concept we are going to use a lot in this course is basically at the heart of statistical mechanics, is the concept of a probability density. And I know I have at least one mathematician in class, so Margot is going to kill me for being non-rigorous between density and distribution, just on probability. Yeah, I'm going to be a bit lax about that, and I will use both of them kind of interchangeably, but the idea is that we have a random variable which can x, okay? So x could be you flipped a coin, whether it is a head or a tail, right? And this random variable can take many, many values. Let's say it can take the value x1, x2. So it can take values x1, x2, x3, let's say up to xk, right? And we can define a probability of observing any of these values. Let's say this is p of x1. Let's say this is p of x2, p of xk. So this is my probability density p. If in the homework you have a head coin toss problem where it can take head with the probability half, it can take tail with the probability half, right? If it is a biased coin, these probabilities will be different. For an unbiased coin, both should be half. So given these things, the set of values a random variable can take, together with its probability density, we can define the average value of the random variable, which is written as x bar. It can also be written using the Dirac bracket notation. This one, okay? And this is given by summing over all possible values it can take. Let's call it xj multiplied by the probability of observing that value, p of xj, and j goes from 1 to k, as many values are possible for the random variable, right? So if we had, yeah, and in the homework problem, basically you work through it to for a couple of examples. So this p of xj needs to follow a few mathematical properties in order for it to qualify as a probability density, okay? First of all, what can you think of? What properties should it follow? It should be between 0 and 1, right? If it is lower than 0, then that's garbage. That's negative probability. It does not make sense. So it should definitely be more than 0, more than equal to 0. If it is more than 1, it means you have not done some sort of normalization. That's what happens. There is a normalization factor which is missing. So it should be less than equal to 1. So P always lies between both of them. What else? It should sum up. The random variable has to take some particular value, right? If the summation of P of xj is not equal to 1 when you go from 1 to k, then you have a problem, okay? And the probability distributions are really, really the heart of StatMech, because that's Boltzmann's distribution is an example of a probability distribution, right? So we'll spend a lot of time in StatMech basically deriving probability distributions and then manipulating them to calculate all sorts of quantities. And I don't think anything else is really needed from a probability distribution for a discrete random variable. So this, what I showed you over here, is a discrete random variable because it can take discrete values, x1, x2, x3, ... till xk. We can generalize this. By the way, if any of the math is confusing to you, the best way to really brush up is Khan Academy. It's the quickest way. He does a really good job of brushing up on things. So if anything is confusing you, go up there. There is also a book by John Straub. Well, that's not online anymore, so I will not say that. Just look up Khan Academy. It will be fine. So that was discrete. We can also think of a continuous random variable. So an example of a discrete random variable was a coin toss, whether it is head or tail. Can you think of a random variable which is continuous?
Temperature.
Temperature is the first one, right? It can change, it can fluctuate between any value, right? What else? Yeah, exactly, right? Or yeah, so most things can be continuous. And of course, if you measure coordinate where it falls, that's continuous in the classical mechanics limit. When you go to quantum mechanics, then you start imposing Planck's constant and everything becomes discrete. You have some uncertainty and things like that, right? So continuous random variable, we can again define probability density, but now we define it as P of x multiplied by dx is the probability that the random variable x lies between x and x plus dx. Okay, this is a continuous probability density. Once again, integral of px dx must be equal to 1. It has to lie somewhere, otherwise you missed out on something. And 0 less than equal to p of x less than equal to 1 for all values of x. It cannot be negative. What is the most famous example of a probability density for a continuous random variable that you all worry about when you're undergrads? That's your hint. Gaussian. Will I grade you on a bell curve? No, I won't. For the new students, I don't know what curve I will grade you on. I can give you all A's if you meet a certain level. So that's, so example, Gaussian probability density, right? And you can see how it looks like. It looks something like e to the power minus x squared by 2 sigma squared. This is always more than 0, right? E to the power something is always positive. This is also always less than 1. Does it follow all the other properties? The second property that we need? It's not normalized, right? So here we need to put in square root of 2 pi sigma square for it to be normalized. This is the Gaussian density. What is an example, a very famous example of a discrete probability density? Or let's say other probability densities. What can you think of? Poisson, but I don't know. It's always forget how to write it. Tell me something that you can write easily. Which is the simplest one? Uniform, even simpler, which is 1 in one, infinite, one place, 0 everywhere. Delta function, right? So delta is a bizarre one. Delta of x, Dirac delta. That's a probability density, right? And it will show up every once in a while. So look up examples of probability density, look up Poisson, look up uniform. In this course, I will not be throwing names except maybe Gaussian. This is the only one I will say. Assume it follows a Gaussian distribution. Otherwise, I will tell you what is the probability density it follows, okay? So you can do this for continuous, you can do this for discrete, but for all of them, you can define the average value. So I wrote down the average value for a discrete random variable. That's going to be summation j is equal to 1 to k xj multiplied by p of xj. For a continuous case, it will be integral xj p of xj multiplied by d xj, okay? And here you have to be careful with dimensionality. If, and this will show up later, okay? So for now, let's just leave it here. So this is the average value of x. It is also known as the first moment of x. If I say something is the first moment of x, there has to be a second moment of x, right? Otherwise, what was the point in calling it a first moment? And I never cared about a second moment. So second moment of x. So let me just write it here. So moments of x. For two of you who are new in the class, all notes are online, all videos are online. This is being recorded on Zoom right now. So don't worry about copying everything. If you want to, that's fine. So moments of x. So first moment is mean of x, or the average value of x. More generally speaking, kth moment of x is the average of x to the power k. Okay, so the second moment of x is the average of x squared. The third moment of x is the average of x cubed. How do I calculate this? Average of xk. You can calculate the average of anything, right? Earlier we calculated the average of x, right? Now we are calculating average of x to the power k. So instead of writing x, we write x to the power k, multiply it with p of x dx. Okay. Oh yeah, and Patrick is correct. You should definitely look up the uniform distribution, because that's the first one we will encounter actually when we do something known as the microcanonical ensemble. So look that up, what it means. So this is the kth moment of x. Let's try to develop some intuition for it. Okay. Let's say we have a Gaussian probability density. P of x is equal to 1 by square root of 2 pi sigma square exp minus x square by 2 sigma square. And let me draw this one, this probability density. So this is x. By the way, I don't know if I told this in thermodynamics, but anytime in my course you draw a curve and do not label the axis, God kills a puppy. I'm serious. Please label your axis. It's as bad as it is. You know, I love dogs, as you know. So anytime you draw a plot, when I was an undergrad, some professor told me that it has just stayed with me, that image. Let's always label your axis. And this is going to look, and this is also known as the bell curve. So what is the first moment, or just the average of x for this curve, for this probability density? 0, right? It is left or it is right. What is the second moment for this one? Huh? It is sigma, right? How do you, he remembers it, but you can calculate it. You have to take this formula and put it over here and calculate it. Okay. What is the third moment for a Gaussian? 0. Why? More rigorously, we are doing integral of x to the power 3 p of x multiplied by dx from minus infinity to infinity. This is an odd function. Is the Gaussian density odd or even? Even. Even multiplied by odd is odd. Integral of an odd function is always going to be 0. Basically, x to the power 2n plus 1 is equal to 0. All odd moments of the Gaussian are 0. Okay.
Can you really use higher moments, like beyond?
In your homework, you are.
I mean, in
Oh yeah, you will suffer. Don't worry. I promise you, there will be moments of suffering. Have you heard that quotation? I suffer, therefore I am, by René Descartes. No, he said, I think, therefore I am. That's my variation of it. I suffer, therefore I am. Okay. And I already told you a little bit about series, summing up series and things like that. So this is like mega super ultra crash course in the math you will need for StatMech. These are the type of ideas which will show up a lot. As I mentioned, partial derivatives do not show up that much. Single variable derivatives show up a lot. I'm not going to write down d by dx of sine of x is equal to cos x type things over here, right? You should remember your single one variable derivatives. Integral by parts will be used heavily. Okay, so these are the type of things. In the first homework, I tried to give you a flavor for what the type of math is. Okay. In the remaining 15 minutes, we are going to cover one semester of 684. We can do it. And you'll be like, wait, why was that a semester course? Let's see. If you miss something, we will start next time, because next time I really want to start with StatMech. Let's do Any more questions about math or what you think you might need to know or whatever? So, thermo. One way to think about thermodynamics, one way to start with thermodynamics is to think how you're taking a system and changing it from a certain state A to a certain state B, right? When you do such a process, let's say Q is heat given to system. So that's going to be integral of delta Q, which is path dependent, right? You might go from A to B, and this is some abstract space, some coordinate 1 and some coordinate 2. I don't know what these coordinates are. Okay, they could be pressure, volume, temperature, whatever you want, some abstract space. And you have one path where you go from A to B. You have another path where you go from A to B. These paths are going to have different values of Q. The heat that it needs to take is going to depend on the path. And again, the best example for that is, who should I go for? Vanessa is sitting over here, and Vanessa drags me from this room to the room above, right? And whether she gets very angry and just kicks me, and I go to the room above, I will get very, very hot, right? I will probably burst with energy. Versus Vanessa is nice to me and kind of gently drags me from here over the staircase. The heat will be different, right? So the heat really depends on the path. The work that Vanessa has to do on me in order to take me over the stairs versus just kicking me through the roof is also going to depend clearly on that, right? In the kicking me through the roof example, she has to do a lot of work on me. Work, which is also going to be delta W, is path dependent. The amazing thing though, is that their sum is not path dependent. That is a state function, okay? That is known as the, what is it known as? Internal energy. It is a sum of kinetic and potential energy, okay? Internal energy is not the same as only potential energy. Internal energy is a sum of KE plus PE. So in other words, if we think about differentials, the sum of delta Q plus delta W is not a delta E, but it is a DE. The change in going from A to B does not depend on, in internal energy, does not depend on what path you take, okay? It's a state function. This is basically conservation of energy. And you can actually prove this from something known as Noether's theorem. We are not going to do that. Anyone knows who was Noether? First name? Emily. You know her story? She had to act like a man, right? She had to dress like a man, put on like beard and things like that, and write emails to Gauss. Oh, dear old buddy Gauss, how is it going? You know, and basically she did everything as a man because 200 years ago, women apparently could not do mathematicians. It's terrible. So Noether's theorem can prove this. You can go and see how it is done. And we are not going to do that in this class. So E, this internal energy is our first example, is one example of a state function. Anytime we have a function, we have variables, right? Something the function depends on. Here I wrote coordinate 1, coordinate 2. This internal energy can be written as a function of any 3 coordinates. It could be NVT. It could be NVS. Doesn't matter. Any 3 coordinates. You can have the internal energy expressed as a function of those 3 coordinates. However, there is something very, very special about these 3 coordinates that these coordinates do not follow. So the point I'm trying to make here is if you know the value of NVT, you have defined the state of a function, okay? And this is something, especially those who took 684 or have read Chandler's chapter 1 should appreciate better. If you know NVT, you can calculate anything. You can calculate E. But is that all that is to be calculated, or are we missing out on something? What are we missing out on? So the point being, NVT are sufficient to tell me the value of E, right? Because E is a state function. And in order to describe a state, I need only 3 variables. And so if I know NVT, I got my E. Similarly, if I knew NVS, I'm told there exists a magical function somewhere which tells me the value of E. But what is it that fundamentally distinguishes these two? What am I missing if I calculate E as a function of NVT? Think, this is important, and this will be coming up again and again in StatMech. Make a guess. Why did we have to think about entropy? What was missing? We said ENVT is thermodynamically incomplete, right? And don't give me the math, but intuitively, what are we missing? Go ahead. Yeah, what does that mean?
It means the ability to proceed a certain direction with no input.
Exactly, absolutely correct. So if I had value of NVT, N1, V1, T1, and I calculated E1, and if I had value of NVT, N2, V2, T2, and I calculated E2, I won't be able to say what direction is the spontaneous direction. That direction, that does not tell me everything, right? The energy itself can go up or down. That's not thermodynamically complete. So, and what it is missing is this variable S, entropy. So in 684, that's why we did not start from this, right? In 684, we started from, how did we start 684? We said there exists a state function S which depends on NVE, right? And this is the grand truth. Have you read Hitchhiker's Guide to the Galaxy? Who here has read it apart from him? He seems to like it. No one else? Have you seen this quotation? The answer is 42. It comes from that book, right? So that book has this problem that people have figured out that the answer is 42, but they have forgotten the question. That's the big challenge. The answer to everything is 42. But this is kind of like that. This is the answer to everything. And we also know the question here, which is physics, thermodynamics, everything. SNVE contains all information you need to know. It has nice properties such that partial S by partial E at constant NV is positive. Partial S by partial N, or which one did we, that one does not, that is of course going to be positive because it's extensive, right? So this is an extensive thing. If you double N, it doubles. And this one is also positive. And the third one is also going to be positive, right? When you double N, entropy doubles. So clearly it's positive. And it is maximized at equilibrium, right? That's something nice about it. Chandler talks a lot about it in the first chapter. Even if you took 684, I recommend you to go and read it. It will help you appreciate it a bit better. It is maximized at equilibrium. So using this, you can calculate the direction of spontaneous change, right? And this then led us, especially the fact that the first derivative is positive, led us to say first derivative with respect to energy is positive, means that S and E monotonically depend on each other, right? As you change E, S increases. This means we can swap these two out. And we can write things as E of NVS, and they are going to be equivalent because the partial derivative is positive, right? So that's why E of NVS is thermodynamically complete. It contains all information that you need to know. So S of NVE is equivalent to E of NVS, and both are thermodynamically complete. And we can, anytime we have a state function, we can write down things like d of s, right? It's a state function. It depends only on the state. So we don't have to worry with the delta. It's just d of s is going to be partial s by partial n at constant VE multiplied by dn plus partial s by partial v at constant NE multiplied by dV plus partial s by partial E at constant NV multiplied by dE, right? Or we could do the same thing with E, and we can write it down as partial E by partial N at constant Vs multiplied by Dn plus partial E by partial V at constant Ns multiplied by dV plus partial E by partial S at constant NV multiplied by ds. These are abstract symbols. In 684, we showed how they connect to common sense things, right? Someone remembers what is partial E by partial N at constant Vs? It's chemical potential. Are you sure?
It's in the energy representation.
Are you sure?
I think so.
Are you sure? Let's go with this one. What is this one? That's temperature. What is the middle one? Partial E by partial V or minus pressure. Are you still sure you want a temperature?
I don't, yeah, well, I mean,
It's mu dm. Okay. So this chemical potential can be defined in many different ways. Here we defined it as partial E by partial N at constant Vs. And we can define it many other ways. The reason why we need to invoke these many other ways is because, so I told you that E of NVT is not thermodynamically complete, right? I said that E of NVS is thermodynamically complete. This one is not complete. But if you're really curious, you might ask, does this mean that there exists no other function, no other state function that depends on NVT, which is also thermodynamically complete, right? Why do we want to do this? Because when we perform an experiment, we can measure the number of particles, right? I can have some way of counting how much coffee I have here. We can measure the volume. I see the size of my cup. Can I measure the entropy of this cup of coffee? No way. I don't know how to do that, you know? I can, however, measure the temperature. So NVT are nicer variables to manipulate as relative to NVS. So we do want, but they don't tell us the direction of spontaneous change. E of NVT does not tell me whether egg dropping on the ground is spontaneous or whether the egg magically jumping up from the ground and reforming is spontaneous, right? That's the point. So is there a state function that depends on NVT and is also thermodynamically complete? What did we do for this? Legendre transforms, right? That was kind of the main thing in thermo. So how does the Legendre transform work? So we know E of NVS is complete, and we want to replace this with some function that depends on NVT and that is also thermodynamically complete. Legendre transform allows us to do that. And the way it does it is to take E and subtract out the partial derivative of E with respect to the variable that you want to remove, partial derivative of E with respect to S at constant NV multiplied by ds, okay? And this has a name. This is temperature. So this actually not ds, just the S here. So now this thing is E minus ts. And we give this a name. And whatever name we give this will be a function that depends on NVT, and NVT are the natural variables for this function, right? So the whole point here is that NVS are natural variables for E, while S of NVE is thermodynamically complete. Therefore, NVE are natural variables for S. This function, we give it a name, we call it A, or the Helmholtz free energy. So A, the Helmholtz free energy, has natural variables NVT, and this is thermodynamically complete. I'm going to stop here. Next time, what I'm going to do is to again start from SNVE, this idea. It's never too bad to refresh it. Once again, show how ENVS is thermodynamically complete, all of this. Look at A and then try to calculate dA, whatever it is, show you that what it looks like, then look at G, remind you of Maxwell relations, and then we will start with StatMech.
What's the intuitive reason for S being a function of NV? Like the point is, you said that you need entropy within the energy because you need an idea of spontaneity.
Yeah.
But
You will
with
get
this-
some more intuition when we get to microcanonical ensemble. So the problem with the Callan approach is it does not give you intuition. People call it the axiomatic approach. And anytime you have axiomatic approach, it's like intuition killer, right? It's like almost like religion, right? You know, like what's the intuition for this idea? No, it's an axiom. Take it and go ahead. But this is where when we do microcanonical ensemble, you will get some intuition. So see you next Tuesday. No, not Thursday, 11 a.m.
I was like, I didn't even introduce myself yet. I was like, I probably should.